Step 6, solving exponential and logarithmic equations. So we're going to take all of our properties we've been working with, our converting from log form exponential or exponential back to logarithmic. And we're going to finally put it all together here in a package where we can see how these things all work with one another. All right, so our first two properties we're going to look at deal with what happens when you end up with an exponential equal to another exponential and their bases are the same. Well, when that happens, you have the property of equality for exponential equations. And we like this because it makes it easier for us to find out if we're looking for the variable, which is a power. I don't have to convert something to a logarithm to find the solution to this. I could just simply equate the powers to each other. So that's what's happening here in this example. So you can read through the key concept there, and then let's apply this. Now, sometimes there's a little work to do to make the bases become the same thing, and that is the case here with our first example of A. If I can make on the right-hand side a base 3, which right now it's a base of 1/9, then I would be able to have two bases of 3 where I'd set my powers equal to one another and come up with the value of x. So let's talk about how we can do that with this 1/9 power. Hopefully we're starting to get more familiar with recognizing numbers that are base values of an exponent. 9, I hope that we recognize as a base 3 number. So maybe what we do is we see that this is the same thing as saying 1/3 squared to the x plus 3 power. And 3 squared is not quite, we're not right there yet with a base 3. We still have a fraction base. But anytime you've got a fraction where a numerator is 1, I can rewrite it as a negative power of your denominator. So in this case, a 1/3 to the second power is the same thing as saying 3 to the negative 2 power, now to the power of x plus 3. So then I get 3 to the x is equal to 3, and then now I have power of powers, which I distribute and get negative 2x minus 6. Here is the goal, to end up with two bases that are the same number, in this case 3. And when that happens, it just means that your powers must be equal to each other. And so I solve for x, and I get x is equal to negative 2. And if I were to check this by plugging it back in, 3 to the negative 2 is 1/9. Does that equal 1/9 to the negative 2 plus 3 power? Well, they are the same thing, therefore they check. All right, so that's what we want to do. When I have just two exponentials equal to one another, this is a nice property to be able to use. Here, 64, 16, they are both base 4 numbers, but they are also both base 2 numbers. So what if we rewrote it as a base 4 number? I'd have 4 to the third to the x power. And this is a base 4 number, is 4 squared to the x plus 1 power. Will it make a difference if we use base 2s? 2 to the 6th to the x power, 2 to the 4th to the x plus 1 power. So different bases, will we get the same number? Well, we get 4 to the 3x power equaling 4 to the 2x plus 2 power here, which means my exponents can be set equal to one another, and I get x equals 2. Over here, 2 to the 6x power, 2 to the 4x plus 4 power. Once again, set the exponents equal to one another. And 2x equals 4, and x equals 2. Do they work? Well, 64 squared is 4,096. And 16 to the third power, 4,096. So yeah, they both work. So there's our property of equality for exponential functions. And we'll get to in just a second here our property of equality for logarithmic functions. All right, we've been working so far with changing exponentials into logarithmics. We've been using this, right? We said this is your bread and your butter. B to the x equal y, log base b of y is equal to x. And that's what we've been relying on. There is another way that we can find values of exponential variables. I don't have to change them into the form of log base by equal x, although that works. Another way would be what we call taking logs of both sides. And again, I will use this when I have a setup that has a base power on one side and a constant on the other. And that's the case here for part A. So what we do is we take the log of each side. Just like if I had, let's say, an x plus 1 or 3x equal to a 6. And I decided that I was going to take 3x, add 2 to it, or multiply it by 2. I'd have to do the same thing on the right-hand side. And those are still the same answer, because I've done the same thing to both sides of the equation. I just multiplied by 2. I scaled it up by a factor of 2. We can do similar things with logarithms. So what is not currently a logarithm, I could make a logarithm. So on the left-hand side of here, I could write this as a log base 10 of 9 to the x power. And then make this one a log base 10 of 35. Now I just use my properties of exponents. And I see that a power of 9, or x, excuse me, is going to come out in front. And I get an x times the log base 10 of 9 is now equal to a log base 10 of 35. And solving for x just simply divides the log of 9. And I get log of 35 over log of 9, giving me my solution here. So it's a lot like a change base formula, 1.62. 1.62. Now, had we done the old-fashioned, let's convert it from exponential to log form. So we'll do that over here. This would have become log base 9 of 35 is equal to x. And now we have a change base formula where we put log of 35 over log of 9. And it's the same thing. So you can choose whatever of those two methods you'd like to work with. Either taking the log of both sides or just go ahead and changing the form. We're going to skip B here and actually go to one that involves a little tweaking before we can do this. So we just said that I want to do this when I have a base value by itself on the left-hand side and a constant value by itself on the right-hand side. So here I've got a little work to do. I've got to move some things around so that I get, there's my base value, e to the 0.25x. So I'm going to have to subtract my 8 over there. And then got to get rid of that coefficient, so we're going to divide by the 6. Now we're at a place where I'm set up to go ahead and make these things become both. I could make them both logs if I wanted to, but we're dealing with a base e, so it might make more sense for us to make them natural logs. And we still have our properties where I have a power that's needing to hop out in front here. And then, let's see, we want to move that natural log of e over to the other side. So I'm going to do that through dividing natural log of e to both sides. And I get 0.25x is equal to the natural log of 2 over the natural log of e. Now, putting this into the equation, or into the calculator, natural log of e, I actually have to physically put in ln of e to the first. So ln of e to the first power, and I get a 1. So I'd have natural log of 2 at 0.25x, because this just equals 1. Then dividing by 0.25, 0.25, and I get x is equal to the natural log of 2 divided by 0.25, and I get 2.77. So, those properties of logs are also working with properties of natural logs once again. But you have to isolate, right? We talked about that when we were talking about chapter 6. We want to isolate, in this case, my base power so that I can work with it. And that's what we had to do by moving the 8 and dividing by the 6. All right. Well, we also have property of equalities for logarithmic equations, where if on the left-hand side is a log of some base b, and on the right-hand side is a log of the same base, but you're taking the logs of two different values, in this case log base 2 of x equaling a log base 2 of 7, in order for them to be equal to one another, that must mean that x has to equal a 7. So this is the same kind of property that was going on with our exponents, but now with logarithms. So here in part A, we want to verify, first of all, that the bases are the same. And they are. So that would mean that what I'm taking the log value of, which means on the left-hand side, 2x plus 8, must be the same thing as what is on the right-hand side, 6x minus 12. So I'm just simply ignoring the log bases, because they're the same thing. I can just set these two equal to each other. Negative 4x, negative 20, x is equal to a 5. And I want to make sure that it works, because I can't take logs of negative numbers, so I want to make sure after I plug the 5 back in to the originals, putting 5s in each of those places gives me a 10 plus an 8 on the left-hand side, or log base 4 of 18. 30 minus a 12 on the right-hand side, also log base 4 of 18. So I get x equal 5. That one works. So that's what we're going to be doing when we talk about the property of equality for logarithmic functions. Look for the same bases. Here's another one. Log base 7s, log base 7s. So that must mean 6x minus 16 is equal to x minus 1. 5x is equal to 15. And x would be equal to 3. Do they both work? 18 minus 16 is 2. 3 minus 1 is both 2. Yep, they do work. All right, so we just talked about a little while ago with exponents that I can make something, or logarithm, yeah, exponents, I can make something become logs. It's the same thing when it's the other way around. What if I'm starting as a log? How can I rework this? Well, I can do something called exponentiating. And it's the same kind of a concept we had where we made something log on both sides. And now we're going to make something with same bases. And what we're going to have here is a log base 7, 3x minus 2 power, and a 2 power on this particular example here. So it's called exponentiating. And we pick a base that we want to make these become powers of. And the best choice for the base we should use is the base of the logarithm. And the reason we do this is because we have our inverse properties of logarithms, which tell us the following. Log base b of some value here. If I were to take that and make it an exponent, then the bases of the exponent and the base of the logarithm are the same thing. This just became x. That's one of our inverse properties. Well, we're going to do the same thing here. I'm going to make 7 become my base. I'm going to make log base 7 of 3x minus 2 is now my power. And on the right-hand side, 7 is my base, and 2 is my power. So these two things, this and this, are just now becoming exponents, thus exponentiating. Because 7 of my base and 7 of my log base are the same, that means this whole thing just becomes 3x minus 2. And here, 7 squared becomes 49. Well, now we're ready to solve. 3x equals 51, and x equals 17. So that's called exponentiating. Once again, I could also use the old-fashioned method where I just change the form. So it's in log form. I changed it into exponential form. I get 7 squared is equal to 3x minus 2. And guess what? It's the same thing. I get x equals 17. So that's the process of exponentiating. Some of you guys would probably prefer this method, so you don't have to remember my change of forms here. All right, let's try it on this. I see a base 5, so I'm going to make this become log base 5 of 3x minus 8 as power of an exponential base of 5. And I'll have 5 squared on the right-hand side. So that means 3x minus 8 is equal to 25, so 3x is equal to 33, and x would equal 11. All right, let's actually see what happens when I have multiple logarithms working together, but they are not equal to each other, and I have maybe a constant on the right and 2 logs on the left. How do I work with that? This is going to be using our properties to solve logarithms. And in some cases, we have to be careful because we will end up with what are called extraneous solutions. So our domain of our logarithmic function, if you remember what the graph looks like, it doesn't include all the real numbers. So real quick on the graph, remember if I had this, my log function looks something like that, where I have a vertical asymptote, and my x values are going to be, in that case, everything greater than 0. So I can't just pick any old value of x. Negatives won't work, because they won't generate the log graph over there. And so I have to make sure that when I'm looking for these extraneous solutions, when I get values of x that put in a negative value for a log, they will not be a part of my solution. All right, so what do we do now? I can't do my cool little trick here on this part A where I can say, oh, log base 6, that must mean 3x equals x minus 4. Well, that's not going to happen because actually they are adding together right now. They're not equal to each other. Plus, I have just 2 on the right-hand side. But what I do have here is a log property going on with those 2 logarithms. I'm adding them, so I remember that an addition becomes the product. Do a little simplifying here, we get log base 6 of 3x squared minus 12x. So that's what I'm taking the log of. This is equal to a 2. Here, now you're left with the choice. Do I want to exponentiate? Do I want to just simply change my form? Regardless of which method you do desire to go with, you're going to get the following. 6 squared is equal to 3x squared minus 12x. And now you get 0 is equal to 3x squared minus 12x minus 36. And here I could divide a 3 out of everything. X squared, 4x, 12. Factor it. X minus 6, x plus 2. And then because of zero product property, I have 2 choices. X equals 6 or x equals negative 2. I'll just need to make sure they both work. Let's put a 6 in there. 3 times 6 is 18, that works. 6 minus 4 is 2, that works. I'm not literally looking for values, I'm looking for positive or negative is what I want. So logs of positive is what I'm looking for, and both of those are generating a positive. If I put a 6 in for x, what if I put a negative 2 in for x? Well, on the left-hand side, when I put a negative 2 into that guy, I get a log base 6 of negative 6, and that does not work. So, it's extraneous, only solution is x equal to 6. let's do the same thing here. Log. These are base 10s. 5x times x minus 1. So I get log of 5x squared minus 5x equals 2. 10 squared equals 5x squared minus 5x. 0 equals 5x squared minus 5x minus 100. Divide everything by 5. 0 is equal to x squared minus x minus a 20, giving me an x minus a 5 and an x plus 4, giving me solutions of 5 or negative 4, of which negative 4 is going to be extraneous, and I get x equal to a 5. All right, we're going to try another one here that complicates things just a little bit. Let's add some space. Let's try this. What if we had a problem that was log base 4 of the quantity 2x plus 1, and we were subtracting a log base 4 of an x minus 2. So remember, I can have logarithms on both sides of the equations. My goal is to put those logs together somehow, use a property to write them as a single log. So I guess another example is I could have this whole logarithm actually over here as a plus log base 4 of x minus 2. And in that case, if that was my original setup, I would want to make sure I'm subtracting it to the left side so that it looks like we have currently. All right, anyway, with a subtraction problem, we have quotient 2x plus 1, x minus 2 is equal to 1. And here, we're again at the point where we're ready to just change our form. So this is going into exponential form. It's 4 to the first is equal to 2x plus 1 over x minus 2. And then here, it's second proportion. So get rid of that x minus 2 on the bottom. So multiplying by 4 times x minus 2 gives me just 2x plus 1. 4x minus 8 is 2x plus 1. 2x is equal to 9. X is equal to 9 halves. So in this case, we ended up not with a quadratic because we weren't squaring anything. We just got a single value of 9 halves. And putting 9 halves into both of the original parts of those problems would give you a solution that works. So there's just another one, a little bit different flavor. Actually, you know, we've already taken a look at this stuff. Depositing 700 is a little bit of a review problem. We're depositing 700 bucks. There's our initial amount, our initial principal. We have a rate of 0.0275. How long does it take if we're going to get the following? Quarterly compounding. So quarterly again means 4 times in a year. So we'll just run through this example here. This is the problem that sets up as a sub t is equal to a sub 0, 1 plus r over n to the nt power. N representing how many times in a year we're compounding, which is 4. So we have 1,000 bucks. Oh, I'm sorry, I didn't read this. We're wanting to reach $1,000. Okay, so we're trying to make 1,000 become our final amount. We started with 700. We have 1 plus 0.0275 all over 4 to the 4t power. All right, we're going to divide that 700 over there onto the other side. We get 1.43 is equal to, and then 0.0275 divided by 4, and then that plus 1 gives me 1.0069 to the 4t power. All right, we're looking for an exponent, which means I could make these both become logarithms if I wanted to. I could just change my form, and if I changed my form, I'm going to get log base 1.0069 of 1.43 is equal to 4t. And then I have a change base formula of 1.43 log 1.0069 is equal to 4t. And I would have to end up dividing by my 4 here. So log of 1.43 divided by the log 1.0069 is 52.02. And then divided by t, divided by 4, I get an approximate value of 13 years. So it's going to take about 13 years for our $700 initial investment to get to $1,000 at that interest rate at that compounding period. So a little review there on some of our math problems. Hope that helps.